And then it was published in September, also in Microscopy Today. And in that paper, we published our results of blood clots in dinosaur bones. How many of you have heard that there are blood clots in dinosaur bones? Okay, I'm glad you're here today because you're going to see something new. That video is on our website and it's on your website, so you can watch that and learn about that work. That was all Triceratops. And so this is a picture of one of those bones. This is a Triceratops. I think this is horn material. And it has been thin sectioned. So we take a bone like this, we put it in a special machine, and it shaves it down to about 1/3 the thickness of a human hair. So it's a very laborious process, but we get it thin enough so that we can examine it under the microscope. Now, you see the bone is kind of brown, yellowish brown here. And this ages over time. Even 100 years in the ground would cause this kind of bone material to kind of darken a little bit, right? But this here is excessive. See all this black stuff? And it's all in the canals. These are blood vessel canals that go through the bone. So you have canals in the bone, and the blood vessels and the veins and the nerves actually travel together inside those canals. This is all clotted blood, folks. It's all clotted blood. And so what we showed was that the blood, which has iron in it, is still present in the canals. This is a bright field picture, so now we're pushing light through that thin section of bone. So this is all light coming from the microscope, and you see how light it is. But this is all black. This is a blood clot. And look at how much of the total volume of the vessel canal is cut off. This is rare, actually, to see this much of an opening in some of these clots. Most of the clots that we find are fully filling that lumen, that opening of the canal. This is what it looks like under a regular bright field microscope. But then we used a special microscope that works with UV light. It's very dangerous for your eyes, so we have to really protect ourselves. But the advantage of the UV light is it makes the iron autofluoresce. What does that mean? Glow, right? All tissue glows if you hit it with a certain energy, a certain wavelength of light. All tissue glows, okay? And so we take advantage of that property and we hit it with UV light, which makes the iron react, autofluoresce, give off its own light. And it does it at a characteristic wavelength. So we know we have iron, and it's right here in the canals. Now, I'm not going to take a long time to talk about it, but there is a theory that iron preserves the soft tissue. How many have heard of that? The iron preservation theory, a couple of you. In any event, it's the big argument that solves the why is the soft tissue still here problem. Yeah, because it's a problem, right? Why is dinosaur soft tissue a problem? Because they're 68 million years old. Make a peanut butter and jelly sandwich next week, put it in the backyard as an experiment, and measure how long it takes for that soft stuff to go away. And you'll get an idea. We know innately, right? Soft tissue doesn't last. So it kind of begs the question of age, doesn't it? So this is then the work that we published in Microscopy Today in September. We found it in the horn, the rib, and the frill. And in fact, it was 6 individuals that were separated from each other in the digs who had clots, all Triceratops. Well, we've done more work of that on that, and I'll show you that in a second. But I've discussed a little bit of the significance of why this is important. There's a medical condition that you may have heard of called disseminated intravascular coagulation. Who would repeat that to me? No takers, right? It's hard. It's a known medical condition in the medical literature that happens when a human drowns. Wow. When there's a human drowning victim. When they die through drowning, their blood stays clotted in their soft tissue and in their bones. You get clotted blood when you die from asphyxiation in water. If you survive and you're revived in the ER, which happens a lot, you bleed out. Why? Well, there's this process of coagulation that you've heard about. It's a one-way reaction. It's dependent on the reactants. When clotting begins, it's a one-way reaction. It goes till all the reactants are gone. And if you die, you stay in that condition. If you survive, it starts to go backwards, and instead of clotting, you bleed out. So now these ER physicians and nurses are trying to save your life while you're bleeding out because they resuscitated you as a drowning victim. These guys weren't resuscitated. So their bones are full of clots. This is important because the clots sequester the iron from what are called Fenton reactions. Don't worry, I'm not going to do chemistry on you today. Picture Pac-Man running around eating those pellets. Fenton reactions needs water to create the Pac-Man that go and eat the tissue. And boy, does it eat the tissue. How many of you had a steel bumper in Detroit during the winter in the past? You know what I'm talking about. Iron eats the steel. Imagine what it does to soft tissue, and it is highly destructive. So we're showing that the iron is left in the canals. It didn't migrate out of the canal into the bone, right? You can see that, can't you? So the iron was unavailable, and if these vessel canals are clotted up and blocked, the water is not available. Water is required for Fenton reactions. So we think we have a great answer to this iron experiment that I wish I had the time really to talk about the experiment, because it is really not the kind of experiment you'd want to conduct to prove that iron is the answer. Everybody's acting like iron is the answer, but they haven't proven it. In fact, the structures that I am going to show you today, that nerve that you just saw, iron doesn't affect it. So it's hard to explain this iron experiment based on the findings that we're making. So we think we're making headway scientifically, and we think that's important. Why do I mention all that? Because we decided to process some Nanotyrannus bones that we collected in Jordan, Montana. May of 2016. We collected a rib, and we collected a vertebra, rib and a vertebra, and we thin sectioned those like I just showed you, and you can already see some of the black in there, can't you? So we found clots in Nanotyrannus. Again, this is a bright field picture, but I'm using both the UV and the bright field at the same time. So you see the light coming through the bone, and then you see the iron reacting. If you turn off the bottom light, it looks like this, and I kind of made it monochromatic so it's more easy to see. But all of this iron in here is returning a signal saying, I'm here and not here. See that? So Nanotyrannus is behaving the same way as all those Triceratops specimens did. Here's another shot of that. There it is, monochromatic. Look at all this beautiful iron just pooled in here. And it didn't cross the barrier into the bone. It didn't migrate into the bone. So what preserved the tissues if it wasn't the iron? This is from the rib. And so you see a beautiful bifurcation here in these canals. So blood vessels, blood veins, and nerves were traveling in here. And now you can see it reacting to the UV. You see a little point here at the end of this, and that shows up dramatically when you just do the epi-illumination. So we're getting really good corroboration here from all of our specimens that they are responding to this technique. So there's a lot more work to do. We want to analyze this. Someone was telling me, and I can't remember who it was, they said, I showed this work to a retired ER physician, and he started naming all the products in here. He had names for everything in there. So I really want to meet that guy. So now we have corroboration 200 miles away from each other of clots in 7 different organisms that are separated.